So what we have done is we've looked at the geometric mean situation, is kind of what I call it. It's when you have a right triangle with an altitude drawn to the hypotenuse. So in that situation, here's your right angle, altitude drawn to the hypotenuse. We're going to call these sides A and B. The hypotenuse is C, and C is made up of two pieces, D and E, and then we have the altitude, which we'll call F. And what we know in this situation is that there are three pieces that are geometric means. I picture this as kind of a duck foot. Here is the webbing for my duck foot. The bones of the duck foot, which are here, here, and here, are the means. The pieces of the webbing, which are E, D, and C, are the extremes in the proportion. So my geometric means always go in the lower left and the upper right position. Since A is a mean, A goes in that position in a proportion. What is A the mean between? E and C is correct. And here's kind of the way I picture that, and I've tried to teach you to picture it. I look at the two pieces of the web that share that endpoint, because that's where A comes down to. It comes down to that point. That's where it hits the web. The two pieces of the web that hit that point are E and C, which is that whole hypotenuse. So A is the mean between E and C. Now, in the next geometric mean proportion, we'll work with B. B is a mean as the other leg there. And what is it the mean between now? D and C, yes. And again, we can use that same picture as in, here we have B coming down. This is where it hits the webbing. And the two pieces that hit the webbing there are D and C. So B is the geometric mean between D and C. Now the last geometric mean is F. So we're going to put F in its own little mean proportion. Here is F as the geometric mean, so it holds the lower left and upper right position. And it is the mean between E and D. And again, we can take a look at what are the pieces that come down and hit F at that point right there, and they are E and D. Okay, because that's where F hits the webbing, is between E and D. So we have then E and D. All right. We are going to use this triangle for our theorem. We're going to prove the Pythagorean theorem using this triangle. Our theorem number here is theorem A2, the Pythagorean theorem. Okay, the two pieces we're going to use, and let me go ahead and state the theorem first up. I guess I haven't done that yet. The Pythagorean theorem says that the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. So in this situation, given this diagram, we are going to prove that a squared plus b squared equals c squared, which is the very common way to state the Pythagorean theorem. To do that, we're going to use these two proportions. These two proportions, if I do the means extremes property, are a squared equals e times c, and b squared equals d times c. If I add these two equations together to get a squared plus b squared, I will have a squared plus b squared equals EC plus DC. Since C is a common factor, I will factor C out, leaving C times E plus D. If you look at E plus D, take a look over here, E plus D. What is E plus D? C. So since E plus D is C, this is the same thing as C times C, which is C squared. So, Pythagorean theorem, a squared plus b squared has to equal c squared. The sum of the squares of the legs of a right triangle has to equal the square of the hypotenuse. Now, working with the Pythagorean theorem, anytime you have numbers where a squared plus b squared equals c squared, it's called a Pythagorean triple. Some numbers that work like that are 3, 4, and 5. Because 3 squared plus 4 squared equals 5 squared. Check it out with me. 3 squared is 9, 4 squared is 16, 5 squared is 25, and 9 plus 16 is equal to 25. So a 3, 4, 5 is a common right triangle. Anytime you have a Pythagorean triple, then you have side lengths of a right triangle. So another common right triangle side lengths are going to be 5, 12, and 13. That also works. So if we take 5 squared plus 12 squared, we will get 13 squared. Those are just two examples of Pythagorean triples. 5 squared is 25, 12 squared is 144, and 13 squared is 169. 25 plus 144 is 169. So again, that would be side lengths of a right triangle. The interesting thing about these Pythagorean triples is, if I double all three of these lengths, 3, 4, and 5, I make it 6, 8, and 10. It still is a Pythagorean triple. 36 plus 64 equals 100. 6 squared plus 8 squared equals 10 squared.
What about like 4, 5, 6?
It does not work. You can check it out for yourself. 4 squared plus 5 squared will not equal 6 squared.
They all have to be.
They're only called a Pythagorean triple if the squares of the smaller ones added equal the square of the larger one. That's the only way they're called a Pythagorean triple. Okay? Now, you wouldn't have to multiply by 2. You could multiply by 3 or 4 or 5. It does not matter. You still get a Pythagorean triple. So this gives you an infinite number of other Pythagorean triples. So 6, 8, 10, we can multiply them all by 3, 9, 12, and 15. Those are Pythagorean triples. So this gives you a family of Pythagorean triples. As does 5, 12, and 13, the same thing. If I multiply them all by 2, I have 10, 24, and 26. Another Pythagorean triple. Now there are other Pythagorean triples, but I'm going to stop with that idea right there. It's enough that you kind of understand what it means. Now, an example problem, and then we'll leave the Pythagorean theorem and let you work on your assignment. So an example problem. Here I am looking at page 292. And I see number 9 is a rectangle. So I have a diagonal drawn in this rectangle. How do I know this is a rectangle? The sides are opposite sides are parallel, and what else? One angle is a 90, which means all of the angles will have to be a 90, right? So this is a rectangle. I also have a diagonal drawn in here. This is 7, this is 24, and they want to know what is the length of that diagonal. Now, if this side length is 24, opposite sides are congruent. So this side length will also be 24, and now we're working with a right triangle. So we can use Pythagorean theorem. You have to have a right triangle to use Pythagorean theorem, which means the legs are 7 and 24. Notice the legs form the right angle. When you have a right triangle, the legs have to be shorter than the hypotenuse, and the legs form the right angle. Okay, so my legs are 7 and 24. 7 squared plus 24 squared equals x squared. So 49 plus, you have a calculator, 24 squared, 576 equals x squared. So now I add those, which is going to give me a 625. And now the question is, what number squared is 625? So we're going to do the square root of 625, and when we do that, we think factor tree. So here off to the side, let's look at the factor tree for 625. I know that 5 goes into that 125 times. And I know that 5 goes into 125 25 times, and I know that 25 is 5 times 5. So I have 2 pairs of 5, don't I? So the square root of 625, I'm going to give myself a little more room here. The square root of 625 will be the square root of 25 times the square root of 25. So 5 times 5, which means that this length right here is 25. So we have another Pythagorean triple, don't we? It's 7, 24, and 25. 7, 24, 25 is another Pythagorean triple. Okay. So that's the basic idea. Let's stop this.